When a solid dissolves, that's an equilibrium process. So if we're looking at an ionic compound dissolving in water, say sodium chloride dissolving in water, we have ions dissolving and going off into solution, and there are also ions coming back and recrystallizing. So we can, because this is an equilibrium, we can write an equilibrium expression for this, but instead of just calling it the equilibrium constant, KEQ, we call this the solubility-product constant. It's the equilibrium expression for a chemical equation representing the dissolving of a solid of an ionic compound. So remember that the solids are omitted from the equilibrium expression. And so if we have a large KSP, that means we've got a lot of product, a lot of the ions. If we have a small KSP, we have very few ions, and that means that the compound is not very soluble. So writing expressions for this, you need to start out with the chemical reaction showing how this thing dissolves. That may or may not be given to you in the problem. So this would be finding the equilibrium expression, the KSP for barium sulfate. So barium sulfate solid dissolves to form barium ions and sulfate ions. KSP is equal to, same thing as for the equilibrium constant, barium concentration times the sulfate concentration. We don't divide by this because it's a solid. Solid concentrations don't change, and so we leave them out. It's not a solubility product, it's called an ion product, but this is the same thing that we were talking about with KW for water. Right? We said that H2O liquid plus H2O liquid can form hydronium ions and hydroxide ions. Remember that from yesterday? So one is acting as an acid, one's acting as a base, forming hydronium ions and hydroxide ions. If we write an equilibrium expression for this, we call it KW because it's for water. Water's kind of special. It'd be the concentrations of the products. So the concentration of H3O plus times the concentration of OH minus divided by the reactants, but the reactants are a liquid, and so they don't get included. And so that's where that comes from. It describes the ionization of water. This is a solubility product constant because it describes solubility. This is the ion product because it describes the ionization, formation of ions. KSP values are not something that you memorize. You look them up in a table if you need them. Here's a table from your book showing a bunch of different ionic compounds, their formulas, and here are the solubility product constants. Most of these are quite small numbers. Some of them, like this one, copper 2 sulfide, 10 to the minus 36. That is very, very insoluble. So let's write expressions for KSP for each ionic compound. First, we have to write a chemical equation showing what's going on when this dissolves. So AgI, you just write the formula for that compound as a solid, and then you put the double-headed arrow, because this is an equilibrium, and then you write the two ions separately. So this is going to form silver ions, and those will be aqueous, and iodide ions, and that'll be aqueous. Now our solubility table, the rules told us that this is insoluble. Everything dissolves a teeny tiny bit. You can still write a KSP expression for it. So there's our chemical equation describing this, and then we say, well, KSP is going to equal the concentrations of those products. There are no coefficients, and so we have no exponents. We leave this reactant out because it's a solid, its concentration doesn't change. It's either there or it isn't. Let's do this one. This one's a little more complicated. CaOH2. So, calcium hydroxide, solid. What ions does that form? Calcium ion. Not H2O. 2OH negative. So the two ions here are calcium and hydroxide. There are two hydroxides, and so I need to show two hydroxides over here. This is why you have to write out the equation, the chemical equation, because we can't forget about this 2. So then for the expression KSP, it's the products. So I've got the concentration of the calcium ion, the concentration of the hydroxide ion, but the concentration of the hydroxide ion is squared. Yes?
So when you were referring to the solubility product and iron product, because it's soluble, this would be a soluble product.
That's a good question. So we're talking about a solubility product. That does not mean that these compounds are soluble in the sense of the word that we've used before, where a lot of it will dissolve. So most of the things that we're going to be looking at here are very insoluble. Like here's calcium hydroxide. Its KSP is a very small number. So that what that tells us is that if you try to dissolve this, you're going to have very, very small amounts of calcium and hydroxide. And so for most purposes, it's insignificant, and we say it's insoluble. Does that help? So we kind of lied to you earlier when we were talking about soluble and insoluble. There's not a hard line. It's either insoluble, doesn't dissolve at all, or it dissolves completely. Things that are soluble do have their limits. We looked at that. The solubility depends on temperature, and it's different for different compounds. And then even insoluble compounds will dissolve a teeny tiny bit. So we looked at a graph of comparing solubilities of different compounds in 100 grams of water. The solubility is the amount of compound that dissolves in a certain amount of liquid. Often it's how many grams per 100 grams of water. We can talk about molar solubility. That would be moles of compound that dissolve in 1 liter of solvent. And so that would have a unit, moles per liter, or molarity. We can calculate that from the KSP, and we typically abbreviate that as S for solubility. So let's look at this one. Silver chloride is considered to be insoluble. But if it dissolves, it's going to form 1 silver ion and 1 chloride ion. And look, you can look this up in the table. The solubility-product constant, 1.77 times 10 to the minus 10, very small number. So this reaction only goes to the products a teeny tiny bit. We're asked to calculate the molar solubility, which would be how many moles of silver chloride will dissolve in a liter. So we kind of have to think through this, because you can't just say, well, what's the concentration of silver chloride, because that's a solid. We're looking at how much dissolves. Well, if 1 mole of silver chloride dissolves, how many moles of silver ion do I get? 1. And how many moles of chloride ion do I get? 1. So if the molar solubility was 1 mole per liter, then the concentrations of each of these would be equal to the molar solubility. Okay with that? So S, how many moles of this per liter dissolve. This is a 1-to-1 ratio. When one of these dissolves, I get one of those and one of those. And so I can say that at equilibrium, the concentration of silver is equal to S, and the concentration of chloride is equal to S. So the concentration of silver ion is equal to S. Let's make those look like S's instead of 5s. And the concentration of the chloride ion is equal to S. We're taking pure water, we're putting sodium chloride in it. There were no chloride ions, there were no silver ions present to start with. They all came from this, and they came in pairs, and so their concentrations have to be equal to each other. What's the solubility product expression for this? KSP equals what? Well, it's the concentration of the products, right? The silver ion concentration times the chloride ion concentration. We leave the silver chloride solid out because it's a solid, doesn't change. Well, we said that this was equal to S and that was equal to S. Let's substitute those in, and then we get KSP equals S times S, which is S squared. Well, what does S equal then? The square root of this. So if I take the square root of this, I'm just going to get rid of that because that's messy in the middle. And I take the square root of this, they're equal, right? So I end up with S is equal to the square root of the KSP. I've been given the KSP. Sometimes you might have to go look it up. 1.77 times 10 to the minus 10. And so make sure you know how to tell your calculator to do this. On mine, I do the square root button, 1.77e negative 10. .33 times 10 to the minus 5. And the unit will be molarity. Any questions? Let's do another one. Calculate the molar solubility of calcium sulfate. Okay, we're not given any extra stuff here. We need to think about how does this dissolve? What's the equation that describes this dissolving? Well, calcium sulfate, solid, is going to break into two ions, calcium ion and sulfate ion. I want the molar solubility, we'll call it S. The molar solubility would be how many moles of this dissolve per liter. If 1 mole of this dissolves per liter, then I'm going to get 1 mole of calcium per liter and 1 mole of sulfate per liter. So the concentrations of each of these is equal to S. KSP equals the calcium ion concentration times the sulfate ion concentration, which is S times S, or S squared. S equals the square root of KSP. What's KSP? We have to look it up. On an exam, I'd give it to you. either in a table that you could refer to, or actually in the problem like that previous one. But homework, we make you look stuff up. So here's calcium sulfate, CaSO4, 7.10 times 10 to the minus 5. 7.10 times 10 to the minus 5. So square root of 7.10 times 10 to the minus 5. Let's go with the same number of sig figs. 8.4261 times 10 to the minus 3. We can round that to 8.43 times 10 to the minus 3. It's a concentration, molar solubility, moles per liter. Any questions? That's a very small concentration. So we would consider calcium sulfate to be insoluble because it doesn't dissolve very much. The previous example is silver chloride. It was even smaller. It was what, 10 to the minus 1, 2, 3, 10 to the minus 5. Very, very small. Any questions?